Okay, so now let's look at a practical example where we are going to use non-blocking calls. Let's consider a simple example. This is distributed histogram updation. Okay. So histogram updation everybody knows, right? You have an array of values and you just want to count how many of each value there are. So you just keep a histogram, an array, and you go and increment the corresponding entry, right? As simple as that. So you could use it to count words that have appeared in a document and so on. Okay, so what we are going to consider over here is, so we'll just deal with integers, we are not going to deal with words. Let's assume that we have a large histogram, maybe all the words of the English language, right? And you want to count them over the internet or something. So how would you go about doing it? Well, if it's a single processor, it's quite simple. Now in a distributed manner, if you want to do it faster, you would write a distributed program. And let's assume that this histogram is too large to fit on a single processor. So in that case, what do we do? So obviously we want to divide the work. So we'll ask each process to look at some of the data, maybe some of the web pages, and update the entries, right? So now, as we said, the histogram is too large to fit in the memory of one process. So what are we going to do? We are going to maintain the histogram in a distributed manner, okay? Let's first just understand what the problem is. So each processor is going to look at some database of web pages or something, documents, right? It's going to read all of these, it's going to go through all of them. Another process would be looking at another set of documents, okay? Now the histogram is too large, so a part of the histogram resides on this node, a part of the histogram resides on this node. And now when it reads the word, of course, the word is not necessarily going to be in its own local histogram, right? It may be a word which belongs to the histogram of the other table. So in that case, what will it have to do? It will have to send the information to the other processor that this particular entry has appeared, so please go and update it, right? So the other processor will take care of it. So each processor will be owning a part of the histogram table, and each processor will be reading a large input, right? And based on the entries, it's going to send the data to the appropriate nodes to update their histograms. Okay, the problem is clear? Let's design it, right? So we are going to, instead of words, we are going to deal with integers, right? We'll keep life a little simple. So let's say that you know the size of the alphabet, right? Or the total number of entries in the histogram, right? Let's say we know that. Okay, that's num entries. So first of all, we want to divide this up amongst the processors. So how do we divide it up? Again, for simplicity, right now what I'm going to assume is that num entries is a multiple of num ranks, the total number of processors. Okay, let's just assume that for simplicity. Otherwise, we'll have to get into boundary cases, but that's not really what we want to talk about. We want to talk about non-blocking calls, right? Now, you have your main function, right? We are not going to write each and every call. First of all, I'm going to have to allocate my local histogram, right? So how do I allocate my local histogram? What is the size of the local histogram? So local entries, what is the total number of local entries? That will simply be num entries divided by num ranks. I'm assuming that you've already made call to Mpi rank, Mpi init and so on, right? So you know the num ranks, okay? Yeah, so that's the total number of local entries. So you go ahead and allocate this. So let's say hist is equal to int. Let's deal with integers only. Let's assume that all the data is integers, right? So you basically allocate size of int times the number of local entries, right? So now you've allocated your local table. As we said, right, it's perfectly divisible, so we don't have to deal with boundary cases. Okay, well, I have to initialize histogram with zeros, right? So I'm not writing the code for that again. That's simple. You can write a simple for loop to do that. All right, now I read data from a file or something, and it returns a pointer to the data. It allocates the data and returns the pointer to it. So my data is equal to read data from some file, whatever the input that it's responsible for. So now I need to basically look at all the entries of my data and go and figure out where to send that data, right, which node to send that data. So I also know the size, right, how many entries there are, it returns that as well, how many entries there are for my data. So what am I going to do? I am going to run a loop. Let me keep a counter, right, I equal to 0, and while I is less than size, right. So I have to basically go through all the data and send it to the corresponding processor. So while I is less than size, I am going to look at the next data. How do I figure out where this data is supposed to reside? So we haven't spoken about that, right? Let's speak about that a little bit. So the total entries is num entries, and each processor has local entries, number of entries, and local entries multiplied by the number of ranks is equal to num entries. So one simple way is that what I am going to do is I am going to simply allocate the first set of local entries to processor 0. So this is 0 to local entries minus 1, right? These many elements, these are the exact indices, these go to processor 0, then local entries up to 2 times local entries minus 1, right? These go to processor 1 and so on, right? So sequentially I just distribute this. So in this case, I am going through my data sequentially, right? In the ith step, I am looking at the ith element of my data array. Now where do I send this? Where is this supposed to go? How do I figure this out? How do you check where this index lies? If I am given a particular index and I am told that increment this index by 1 because I have just seen this index, how do you figure out where this resides? So if you divide index by local entries, the quotient gives you the processor on which it resides, and if you take the remainder, it will tell you the entry number in that local table. Yeah, so we divided by local entries, that gives me the processor, and now I know where to send it. So I check if P is rank, if it's the same as me, right? So again, we are going to follow the same convention throughout this course, right? Rank will always refer to my rank, num ranks will always refer to total number of ranks, okay? So if P is rank, then what do? Then I go and update, I say histogram. Which entry of the histogram? Well, my data I, take the remainder after division by local entries, right? Plus plus. Yeah. Otherwise, what do? Else I have to post an Mpi send. I have to send it to the corresponding processor. Okay, so I can use an Mpi I send or I can use an Mpi send. Right? In this particular case, we can use Mpi send because it's just an integer, right? The main problem we have in this particular case is that we don't know when some other process is going to send me data, right? I have no idea when another processor has an entry for me and when it's going to send me data, right? So if I post an Mpi receive to receive data, then I cannot do any computation, but I have lots of computations to do. What is the computation that I have to do? I have to read the file, I have to send that data to the other processors, whatever data I receive I have to update it, right? I have some computations to do. So I don't want to basically block on a receive. In this particular example, we are going to look at how to use Mpi I receive, right? Mpi send will use as it is. And this also highlights another important point, that it's not necessary that if you are using an Mpi send, then the receiver has to use an Mpi receive. The receiver can use Mpi I receive. So these can be used in any combination. Okay, it's not that, you know, if you've posted an Mpi send, that data has to be received using an Mpi receive, and if you've posted an Mpi I send, it has to be received using I receive. That's not the case. Okay. All right, so we'll do Mpi send. What do we send? We'll just focus on the important arguments over here. What do I have to send? First of all, I have to send my data I, right? And then other arguments, and then which processor do I have to send it to? I have to send it to processor P. The other arguments you can fill in, right? Okay, I have sent one unit of data. I have looked up one entry and sent it. Now what should I do? Well, I can go back and send the next entry and so on, but what I want to do is I want to overlap the receiving of data with the sending of data, right? Otherwise, everybody will just be busy sending the data. There are multiple issues with that, right? First of all, no node is receiving any data, so there is little overlap. And the second issue is that it may actually clog the network, right? Because nobody is receiving, everybody is sending, eventually that data is going to get stuck in queues, right? Okay, so what I'm going to do is, along with this computation, I want to regularly also check if I have received any data. So how do I check that I have received any data? Well, I haven't even posted a receive, so either I post a receive over here, but this is a while loop. So what I'm going to do is, I'm going to post an MPI I receive before getting into the while loop. Okay, so this is a non-blocking receive into some buffer, right, some integer buffer, MPI any source, okay, and the other arguments you can fill in, but essentially the important part is that I have posted an MPI I receive. Okay, let me also say ampersand request, right, I need the request. Okay, so I post this I receive before getting into the while loop. And now what am I going to do inside the while loop? I am going to test if I have received any data. So I'll pass the request, right, flag and status. Clear? So I sent one item, I did some work, and then I am checking if I have received anything. So this is going to return back immediately, right? It's going to return back immediately and tell me whether any data has been received or not. So I have to check whether flag is 1 or not. If flag is equal to 1, in that case, so I have received some data. So I'm going to update the histogram. Where did this data come in? In buff, right? Some buffer called buf. So buffer modulo local entries, right? Plus plus. Simple. Now what else do I have to do? Now I have to post another receive, because that receive is over, that receive is done, that non-blocking call is over, but I have to receive more data. Okay, so I am going to post another MPI I receive, exactly same as before, ampersand buff, source any, right, and so on. A request, same request, I'll use the same request, because the moment this Mpi test said flag is equal to 1, that request is done, right, that request is over. So that request variable is free now. Yeah.
So what if multiple, like there are multiple receive signals?
You're saying that multiple data has come which matches the receive, so it will give you one at a time.
So the second one will come like in the next iteration?
In the next iteration. You have to post another MPI I receive. When you post the next MPI I receive, when you post the MPI test corresponding to that, it will tell you that the next data has come.
So like even after the while loop, this while loop ends, we'll have to post another while loop.
We'll come to that, right? But let's at least get the high level idea what we're trying to do, then we'll get into the intricacies of small issues that need to be dealt with. Okay, so I post another MPI I receive, that's pretty much it, right? So let's look at the code, at the complete code, this is what it looks like. So at the end you basically call MPI finalize, right, and that's it, you're done. Okay. Now let's start with the issues. First of all, when you've sent all the data, that doesn't guarantee that you have received all the data. There may be more data that you have to receive, right? Let's deal with that first, right? So how do we deal with that? So I'm not going to exit when I have sent all the data. Let me exit only when I have also received all the data. How do I know? Yeah, that's the other issue. So for all you know, I may not even have any data to receive, right? I've posted an MPI I receive, I may not even have any data to receive.
a finished flag, and after someone is finished, he sends it to all the.
Yeah, good. Right, so that's one way of doing it. So who sends to whom? That's important.
Everyone to.
Everyone to everyone. Yeah, that's a reasonable way of doing it. Okay. So you don't know the total number of entries you're going to receive, right? So how do you take care of that problem? So the way to take care of that is that whenever any processor is done, it just sends an end message to all the other processors. Okay. All right. So what I'm going to do is I'm going to have another variable called the num ends, right? How many ends I have received. And how many ends am I supposed to receive? Num ranks minus 1, right? I'm obviously not going to receive from myself, but I'm supposed to receive from everybody else. So while num ends is less than num ranks minus 1, I stay in the loop. That takes care of your second problem also, that after you exit, after you've done all the sends, you have to receive more data, right? So this will not even exit this while loop, okay? All right, but now you have to be a little more careful. Where are these num ends coming? They are coming in the same request, right? We'll send them in the same message. Okay, we'll just keep a different index for it. So how do we keep a different index for it? Maybe we define another entry called end entry, right? And it is defined as num entries plus 1 or something, right? It doesn't conflict with the valid values, right? So it's not a valid integer in the histogram. All right. So now we need to be a little more careful. First of all, when I'm sending data, I can't just send data blindly because I might be in this loop just waiting for the ends, right? So I just check if, okay, another thing we missed out was this I needs to be incremented somewhere, and that's easy. I just increment I over here, right? This is saying that I have sent one more data. So next time I have to send the next data item and so on. Yeah. Okay, let's come back here. So I want to send data only if I have not already sent all the data. If I is less than size, right, I have not sent all the data, only then I go ahead and send all this data. So this is the sending part, right? This entire thing is the sending data or processing input, whatever you want to call it, right? So I do this only if I is less than size. Otherwise, if it is stuck in this while loop because it's waiting for end messages, then it's going to skip this part. What happens after Mpi test, right? If flag is equal to 1, I may have received two different types of messages. Either this buff is end entry or it's not end entry. Yeah, if it is not end entry, then I do whatever I did, right? But if it is end entry, then what do I have to do? If it is not end entry, then I go ahead and update the corresponding entry. But if it is end entry, then what do I have to do? I was keeping track of some variable, right? Num ends. So I have to go and update num ends. Plus plus. And I have to post the Mpi receive again, right? Because this is not the last finished flag that I've received, right? There is one issue that is left, sending the flag. So where do we do that? Okay, so this is where we were sending, right? So I can insert a small piece of code over here. If I is exactly equal to size, that means I'm here for the last time. I have just sent the last message. In that case, I'll run another for loop for j is equal to 0, j is less than num ranks, j plus plus. Okay, I'll also check it's not me, right? If j is not equal to rank, then do another Mpi send. And what do I send in this case? I have to send the end flag, right? So let me have a variable end entry to rank j. Right? What is end entry? End entry is just a variable which stores the end entry flag, right? That's it. Is this clear? So when I sent the last message, this is checking if it is the last message. and I post an MPI send for all the end entries to all the other ranks. Okay. What else are we left with? So now we've sent the end messages. What is important is that we do it incrementally so that you know exactly what kind of things need to be taken care of. One last thing is left. It's a very minor thing, but let's just do that. Before I post this particular MPI receive and this particular MPI I receive, right? Before I post these two I receives. So when I'm done with receiving all the messages and all the ends also, when I'm done with receiving each and everything, then I shouldn't be posting an I receive, right? Actually, I'm going to get out of the while loop immediately. But if I post an I receive and I get out of the while loop, then I'm in trouble, right? There's a pending I receive. So the last I receive should not be posted. So I just check over here. If I is less than size, right, or num ends is less than num ranks minus 1, only in that case I will post the I receive, because this basically says that there is at least one more receive to be done, right? Either there is a message to be received or there is a num end.
How big is the internal queue for the receive?
That's completely architecture dependent. With MPI, you may have some control. Suppose you get data from another node. What does MPI have to do? MPI has to check that who am I supposed to send this data to. So it checks for a matching receive or I receive call. Suppose there is no I receive or receive call which matches this data. If it finds a matching one, it will start putting the data there. But if it doesn't find a matching receive or I receive, what does it do? Then it has to start buffering up. So MPI also has to buffer up, right? MPI has to maintain buffers. It has to keep on storing the received messages until the corresponding receives are posted. So again, everything happens within a limit. So there's a size for MPI library. In lots of implementations, you can specify the size, that this is the buffer space I want MPI to maintain. Architecture is typically not in your hands, right? The network queues, network FIFOs, that is not in your control. So when MPI buffers fill up, what happens then? There are again various things that can happen. Yeah, but one of the things is that you can start blocking the network. So you don't just have output FIFOs, you also have input FIFOs, right? Where data comes into the network and gets stored in the input FIFOs. Then MPI picks it up from the input FIFOs and starts buffering, right? So the input FIFOs get filled up. Once the input FIFOs are filled up, so there is again a protocol, a link level protocol maintained between nodes. So the node does not even receive messages from the other nodes. So if another node has a message to send to this guy, there is again an acknowledgement based protocol that goes on between them. It won't even send the data to this guy because there is no buffer space over here, right? And if another node doesn't even send the data, the other node's output queue is going to get piled up, right? So eventually the network will get congested. Okay. So it's important to keep a flow. That's why you typically don't just do all sends and then do all receives, because that will choke the network, right? The buffer queues will start getting piled up. So you want to interleave them and do them together.